Okay, so now the issue is we have to discretize the equations. We have already done the discretization of space. So the next step is discretization of the equations, and that for discretizing the equations, what is the thing required is that all our equations are differential equations. So we would learn how to discretize derivatives, partial derivatives. That is what we will learn, and using that we can discretize the equation. Okay. So the basic technique used here is and this technique is called finite difference representation, because it's based on difference. So the derivatives are converted in terms of algebraic terms which are based on difference. Okay. So the first thing we have to do is we talk about Taylor series. Okay, and this is going to give us approximate solution. We know what is a Taylor series. This is a Taylor series. Now if you want to find value of function at any point, that is I plus 1. Okay, so what the Taylor series is basically saying, if you have a function like this, right, and like this, and if you want to find out value at this point, right, so you can always find values in terms of this. So this is your x I minus 1, and this you can say this is your x I. Okay, so what Taylor series is telling us, that if you want to find out value at this point of a function, you can find in terms of the value at this point and derivatives at this point. So if you know all the derivatives at x minus 1 and the value of function at x minus 1, you can find the value at x I. Okay, here we are talking in terms of I plus 1 and I. So I may write it as I plus 1, and this as better write it as I. Okay, so this is what we are talking about. So ui plus 1, j is a basically subscript used to show that we are moving in a horizontal line. Vertically there is not a movement. Okay, of course we will talk about that later on, but at the moment we are moving only in x direction. So ui plus 1 is equal to ui plus first derivative at I with respect to x multiplied by delta x, then second derivative with respect to x multiplied by delta x square by 2 factorial, then third derivative at x with respect to x at I, right, and multiplied by this coefficient, and it goes on. This is an infinite series. Okay, so Taylor series is an infinite series. Now the above series gives an exact representation or expression of ui plus 1. Now you can find exact value of ui plus 1 provided you take all the terms into account. So this is an exact representation provided that your series is convergent. So only thing is required is series should be convergent. There are tests for that, you can check up, and because factorial is there, all series becomes convergent, because factorial is a very strong number. When you are dividing by factorial, subsequently all the terms are going to become smaller and smaller, which it means is that only the derivative should not be infinite, right? Whenever there infinite derivative will come, because if suppose you're talking about a vertical function, right, the derivative will be equal to infinite, and if you are going vertically up, you can not define in terms of a previous point. So that is the thing. But we are not talking about those such special cases, right? In fact, if a function is vertical, it is not called a function, right? Function का definition है for every value of x there should be a unique value of y. If you are vertical line, that means for a given x you have multiple values of y's or multiple value of function, so it does not become function itself. Function से भी out होता है. The only thing you, just like you have to control the thing that the thing should not be divisible by 0, similarly you have to see that your function should not have two values at the same point. It's no longer a function, right? So those mathematical, you can say, checks are there, but for the time being we will keep them aside, right? They are important, but they are important when you are actually entrapped in mathematics. Okay, at the moment we are trying to understand what is the way we do it. Okay, so we take an example. We begin with an example that if fx is equal to sine 2 pi x, this is our function. So our objective is to find value of function at x is equal to 0.22, while we know all the derivatives and the value of function at 0.2. So we are moving slightly ahead of 0.2 and we want to find out what are its value at 0.22. Okay, assuming that all the values at 0.2, x equal to 0.2 are known to us. Okay, so how do we go about doing it? We can write this Taylor series. Now you can see on the left side we are calculating value of function at x plus delta x. On the right side everything is in terms of function value is in terms of x, derivatives in terms of x, and then you are multiplying with this difference x square, delta x cube, etc., etc. So what we do, we make a function like this 0.22, we divide in two parts 0.2 and 0.02. So delta x is, this is our delta x and this is our x. You can write the equation for this. If you solve this for infinite number of terms, you get the exact value of function at 0.22. Okay. Now again what will happen, we cannot do the infinite number of terms, so we will do it at different points. Okay, what we will do, we will find the approximation at this point, at this point, and at this point. So what we will be doing, basically we will be leaving out the terms, remaining terms. Though the first approximation is that I say that all these terms, this is my first approximation, all these terms beyond 0.1, I should write here, this is 0.1, this is 0.2, and this is 0.3. So all the terms which are falling on the right of 0.1, I will drop them. Okay. If I do that, that means f x plus delta x is equal to this fx, which means that f at 0.22 is equal to f at 0.2, and this value I already know it. So this is one way of finding out, which means is physically what it means. What it means is that if my function is like this, and we have to find at, suppose the value at this point, in terms of the value of function at this point, then the value at this point is nothing but this. This is my x plus delta x, and this is my x. So of course I get this error. This is the error. What I am saying is only the value at the right, at 0.2 distance from the current value x, 0.2, right, is same as the value at 0.2. So what I am saying is that my function is horizontal after this. Okay, now I can do that. Okay, I will do a second step. Instead of taking the terms up to 0.1, I will take terms up to 0.2. This is my second approximation. Okay, and what does that mean? That f x plus delta x is equal to fx plus derivative of f with respect to x at point x multiplied by delta x. And then you have this calculations which I am not talking about, right? You get this. Now you get a different value of f at 0.22. Now how we are getting this value is, how it is different from the previous one. Let us put it on the graph. Okay, so I wanted to find value at this point, okay, in terms of the value at this point. In the first case I said the value at this point is same as this. In the second case I am saying the value at this point, second point, is calculated like this. So you take help of derivative also. So I know derivative at point x, this is my point x, and this is my point x plus delta x. So in one case I am saying that okay, I will just move from horizontally, I will not take help of derivative. In the second case I am saying that I will move with derivative, and I will take this value plus the derivative here, and I will get some. So somewhere near I am okay. Then we talk about the third approximation, and we take all the terms which are beyond 0.2. So we ignore the terms which are after 0.2. Up to 0.2 we are taking this. So now we are taking three terms, one, this and this. Okay, you can solve this. On the right side everything is on based of x. Derivative, first derivative with respect to x at point x, second derivative at point x, and you are multiplying with change in x. Okay, and what you get is this, right? So, and here you get value there. All the three will give you three different values because they are three different equations, and you can keep on adding as many as you want. But there are infinite terms. So if you want the exact value, you have to go up to infinite, which is not possible. So you have to leave at one place or the other. There is no other option. Now it depends how accurate you want, right? Now this thing can be represented on a graph like this. Suppose this is your graph. This is x equal to 0.2 and it is x equal to 0.22. So in terms of this point, you want to find the value here. Actual value is this. Your function is moving along the dark line. Okay. Now if you take the first approximation, you come just to the horizontally, you move to the. If you make the second approximation, you take this point horizontally plus a derivative at this point, you come up to this. If you take a third approximation, you come here, you not only take the first derivative here, you also take the second derivative here. Take help of that also. So the difference with this will keep on changing. You will have here, you will have here, and then you will have here, right? So this is what is happening. But even after 2 approximation, 3 approximation, you have not reached the exact value. This delta fx, this will remain always. Okay. Now we will use this approach to find the derivatives. Okay. So this is called finite difference formulation using Taylor series. There are 2 techniques, rather there are 3 techniques for discretization. One is called FDM, second is called FBM, third is called FEM. Finite difference method, finite volume method, finite element method. We talk only of 2 here, FD and FEM. We will not be talking about FEM. FEM technique is used primarily in solid mechanics, where the stress and strains are there, materials, how they are performing in that. And in our case, we use a FDM or FBM. Okay. So first we talk about FDM. Now the first formulation we are doing here, it is called first order forward difference first derivative. Okay. We'll talk about how these names come. Slowly it will become clear to you. But we are basically in this formulation, we are trying to convert first derivative into algebraic equation. So that is called its first derivative. So this is our Taylor series, and it is written briefly in terms of, so what you are doing, you are writing u at I plus 1 in terms of ui. Okay. Now all those terms which you saw above, they have been put together here, all the derivative in a summation sign. Now we open this, and actually so you'll see here you are starting from n equal to 1, here you are starting from n equal to 2. So what we have done, n equal to 1 term we have written separately. That's the only thing we have done. Rest all we have put in the summation sign. Now if you look at this, okay, this term will take out here and this we take out here. So we are doing just jugglery, algebraic. Only thing is टेलर सीरीज में you take from here, you take first term out, right, and then you do. So what you can do, you can write this derivative here like this. This is what you get. Once you do it yourself, you will be able to do it, no problem. Simple algebraic. I am leaving out algebraic operations because unnecessarily then I am not able to focus on the real point, which is important. Okay, so what we have done here is, only thing what we have done is we have brought this term, derivative term, on the left side. Now again this A, sum of these series, we have broken in two parts. Now you see that this term was n equal to 2 and the remaining are in the n equal to 3. Okay. Now this term is written like this. Now if you see here, the coefficient of this is delta x, and delta x is the smallest here because you are making it very small. Okay, so all terms here in this section, they are delta x raised to power, you can say 2 to, it will be 2, 3, 4, 5 and so on up to infinite. So the most significant term is this, right, n equal to. So what do? We write it like this, 0 in the bracket as the most significant term. This only shows that what will be the order of error. It's something like this. If you are measuring, let us say, some cloth, you may be accurate up to 1 meter, you may be accurate up to 10 centimeter, you may be accurate up to 1 centimeter, you may be accurate up to 1 millimeter, and so on, depending upon the thing. When you are making a part, mechanical part, it can be 1 millimeter, 1 by 10 millimeter, 1 by 100 millimeter, and so on. You can go up to the accurate. So this is the, you can say, this is the largest term which we are leaving out because actually we will only talk about this. So what we are telling is that this is called truncation error. It's better to give the name here. This is called truncation error. What does it mean? That at this point, terms which are of this order and higher order, they have been dropped. So this is the error in our formulation. So this is called truncation error. Truncation error, why? Because we have left so many terms, we have truncated them, and this truncation error is of the order of 1 because the most significant term has a power of 1. The second term will have power of 2, the third will have a power of 3, and so on. Okay, so the subsequent terms are in any way smaller. So if we want to find out what is the order of error, our error is around the first term. Okay, so now what do you get? You can represent your derivative. Now what is happening? This derivative, first order partial derivative, is represented in finite difference representation plus truncation error. So what you have done? You have converted first order partial derivative into a algebraic equation which is called finite difference representation plus a truncation error. Okay. Now as this delta x approaches to 0, your truncation error goes to 0. So this is actually what you are doing is now your del u by del x is now written in terms of difference in the value of the variable, no derivative on the right side. But this is not an exact representation. This is approximate. So now you are getting the point. Your differential equations were exact. They were capturing the physics perfectly. But because you could not solve them, you have resorted to numerical methods where you have made approximation. So now you have to be watchful that your approximations do not make your system, your result of the actual value, which is your result should be acceptable within the acceptable limits. Right? You have made equations approximate. But what is the guarantee that the result is within the limits? That you have to ensure. So that becomes another exercise we have to. Now, if you want to represent this, you can say if your function is like this. Now what you are saying is the derivative, look at the above equation, derivative at this point, del u by del x at xi. So what I am saying is, if you look at this equation is talking about derivative at this point. Derivative at, why it is moving? The left side is derivative at this point. The right side is also a derivative written in terms of values. Right? ui plus 1 is this value. Ui plus 1 is this value. And ui is this value. Okay? And you divide by delta x. This delta x is this. This is delta x. And so what you are getting is you are able to capture the derivative to an extent. There is an approximation. Now as this point moves to this point, you will move closer to the derivative, the actual derivative. Smaller the delta x, your approximation is better. Okay, are you getting the point? Now, so what we can say that the first order derivative at this point is the slope of line BC by forward difference method. What we are doing is the point at which we want to find the derivative, we are taking a point ahead of it and subtracting it from the previous current point and dividing it by delta x. So what the derivative, this is what you are doing. Look at the equation. You are taking a value at the forward point minus the value at the current point divided by delta x. Right? So what you are getting, you are finding the derivative in terms of forward difference, and that is why this technique is called forward difference. So we are finding the derivative of first derivative. So and forward difference. And what was the error, the truncation, order of truncation error? It was 1, right? So what we call it, so based on these three things, we name the equation which we have got. As the discretization is being done for the first derivative, it is called the discretization of first derivative. So what we have done is discretization of the first derivative. As the truncation error delta 0 delta x is of the first order, it is called first order formulation. As the first derivative at a point this is calculated in terms of this and these points, the current point and the following point, it is called forward difference. So the name is first order forward difference of the first derivative. The finite different formulation of the first order forward difference of the first derivative. Okay, the same thing we can do for in the backward difference method also. We have again first order first derivative, which means we will be talking about only first order derivative, first derivative. Then the truncation error will be of the first order as happened before, but we will be going in terms of backward difference. So how do we do it? Again we take the Taylor series and now we write value at the previous point in terms of a forward point. So all where delta x will become negative. Same thing we are doing. Now delta x is becoming negative. We are going backward. And we are finding the values in terms of. So on the right side are the forward points. Derivatives. All these derivatives at the forward point. The current value is also at the forward point, and we want to find the value at a previous point or on the left side. So delta x is negative. Now you do all these exercise, and I am not falling into it, you actually get this. Here you will get a negative value, but then it is the truncation error. So truncation error can be of both sides, plus and minus. Right? So we don't put sign with it, because this term we are going to leave. This is, of course, delta x here is negative, but your square derivative may be negative also, so this may come out to be positive. This term you are leaving. Okay, this is your truncation error. Truncation error, this is the highest term, strongest term in the truncation series. So the truncation error is of order 1. This is the first order derivative you are finding, and this is the backward difference you are finding in terms of the forward point and the previous point. And this is the equation. You can see here, this is the forward point, this is the previous point, right? And this is the derivative. Okay. So now what we are doing is, you are finding derivative at point B in terms of these points A and B. This is your delta x and this is your delta y, or you can write delta u, or delta f, whatever you want to write. So here what we are doing, we are approximating the slope with a line which is drawn like this, a previous point and a current point, and we draw a slope. Now if we reduce delta x, that means we will move here, we'll move here, and we'll move here. Accordingly our slope will keep on changing, and this I think you have done in your undergraduate classes. You are moving closer to the real slope, but to be exactly on the slope, your delta x should be 0, which creates a problem, because if delta x is approaching to 0, you have infinite number of grid cells. So you are bound from that point. You cannot go beyond a limit. If you cannot go beyond a limit, delta x will be finite. If the delta x is finite, you will have some error. Okay, so this formulation is called, you can say, truncation error. 0 delta x is of the first order, so it is called first order formulation. Derivative this is found in terms of the previous point and the forward point, so it is called backward difference. Okay, and so this is called first order backward or rearward. The rearward word is also used. Backward or rearward difference of the first derivative, and this is finite difference method or finite difference formulation. What have you done? In these cases, you have converted the derivative in terms of approximate algebraic equations. Derivatives are gone. Okay. Now, you can improve upon this. Can somebody make a guess? How will we improve it? We had first the forward difference method, then the backward difference method. Both have the order of error as 1. Can we increase the order of error? That means reduce the error. Is there some technique? Can anybody make a guess? Okay, this is a central difference method and it is called second order of the first derivative. Derivative remains first only. We are talking about first derivative only. The scheme is now central difference. Neither it is forward difference nor backward difference. We are talking in terms of central difference, and the error which we now get is of the second order instead of first order. Okay, how do we do it? We actually add these equations 13.3 and 13.9. That means we are basically adding the equation for the first forward difference and for the backward difference. When we do it, what will happen? Let us look back. You have this formulation here. Okay, and this is the term which is giving first order error, truncation error, and this is backward difference. Look at the now what will happen is this term, the term which is giving you truncation error, that will go away. We are adding 13 point this equation. We are adding this equation 13-19 and 13-3. This equation. The difference between the two equations is on this side the last term is, in one case it is plus, in the second case it is minus, and here the difference is it is u minus 1 or u plus 1, right? The left side is same in both the cases. Okay, so simple addition is being done. Some terms will go away. I am again not going into the mathematics of it. This is what you will get. Left side become double, and what will happen here? You will have ui plus 1 and ui minus 1 will be here. Here earlier there were two terms, uij and uij. When you are finding forward difference, you are subtracting the forward point from uij. Backward difference, you are subtracting ui minus 1 from ui. So basically they were using twice ui. That will go away and you'll have forward and backward point only. Okay, and these terms will also add up. Okay, now what will happen here? So what is happening here is that one set of terms will be with delta x, the other set of terms will be minus delta x. So half of the terms will cancel, the other half terms will add up, depending upon the power of this. Okay, so what you get is here. Now, where you were having 2, 3, 4, all of them added, here you are having 3, 5, 7 only. So 2 is gone, 4 is gone, 6 is gone, they are gone. So only. Now out of this, if you take out the first term, it is this. So you have 5, 7, 9 are clubbed together. This is n equal to 3. This term is left here. Okay. So now you see what is the order of this. This is square. So the first term is of order 2. So this is your truncation error of order 2. So what you have got is this. Derivative at a point is equal to forward point minus the backward point divided by twice delta x. Okay. Now this is your equation. So there are 3 ways by which you can write the first derivative. Forward and the current point and the backward point, and forward and backward point. Okay. The first 2 give you only order of error is 1, but the third one gives you order of error as 2. So that is your better equation, and then you can see it here which one is giving you the best error. This is your central difference, right? And this one is your forward difference, and this one is backward difference, and this is your actual. Right? So this is how these 3 derivatives are going. And obviously, which one will you prefer? The central difference, because this is giving you more accurate result. Okay, without making your equation complicated. You see, in all the equations you have only 2 terms. For each derivative, either you have forward minus the current, or you have current minus the backward, or you have the forward minus backward. You have only 2 terms. Dividing by delta x in 2 cases and twice delta x in the third case. So mathematically all of them are equally complex or equally easy. But in the third equation you find the error is 1 order less. Okay, or you can say 1 order higher, and higher order means your error is less, because you are talking term delta x. So if delta x is 0.1, your error would become 0.01 compared to other. So this is what it is done. Now this is as far as, okay, and then how do you name it? This is a second order, called second order formula, because the truncation error is of the second order. So it is called second order formulation. This is for the first order derivative. It is called, it is based on the forward and the backward point. So it is called central difference. And this method is called second order central difference method for first derivative. Okay. Now we take up one more, another. Now what we are doing is, our equations contain first order derivative as well as second order derivative, and maybe containing third order derivative also, partial. So we have talked about first. We'll talk about the second and we'll not talk about higher ones. By the time you know that how a differential equation is converted into a algebraic equation. So the objective is that. The end result or the objective of this course which I am going, I am not asking you to convert any equation to algebraic equation. Only sample equation so that you know the technique. A real life problem we are not doing from the scratch. Okay. We are only learning how the computer is doing the thing, how the program is running. Okay. So we are now in the second phase. We have written all the differential equation. Now we are writing them into algebraic form. Again we will do some sampling and then we will move on to the next step, okay, of solving them. So here what we are doing, again this is your Taylor series, and this is also the Taylor series. The same Taylor series for the forward point and for the backward point. Now there we subtracted them, here we will add them. Okay. So once you do that, you are going to get this equation. You add it up, and on the right side you get twice uij. So you will get, you see here, these two will be added, this will be added. So these will be added on the right side, these will be added on the left side. What will happen to this? They will cancel each other once you add them. Previously, when the central difference, we subtracted. So they didn't cancel. What was cancelling was this. Now we are adding, so these two are cancelling, and this will remain as it is. Okay. And of course, these terms will also be added up, and what you get is this. So that is all mathematics algebraic. I am leaving it. These two uij, I bring it here, and this I break into two parts. One is n equal to and one is equal to n468. Okay. So I bring this del x square here, and this will become my term for which I want to calculate. Finally, I will get this term will be here, this term will be here, okay, and this is my truncation error. Of course, truncation error is all this together, which is written here as truncation error. You see here the order is square. It's better you do it yourself. I've told you the basic point. Same Taylor series. Only thing you have to, summation terms, you have to bring out one, keep the remaining there. That's all jugglery, small jugglery, you have to do it. Okay. And what you get is this. This is the way to find the second derivative with the order of truncation error equal to 2. Okay. And so what is this formulation called? Here truncation error is of second order. The points considered are central difference because you are considering both left and right. Okay. Of course, the current point is also taken into account. So this is called second order central difference for second derivative. Okay. I have not shown it on the diagram because showing the first derivative is easy, showing the second derivative is difficult in terms of algebraic equation, because first derivative comes in algebraic equation or differential equation, both you can plot. But when you talk about second derivative, the algebraic equation plotting is not possible. I mean, we'll have to, plotting is possible, undoubtedly. You have, what is the equation? You have this. But how will it look physically on the diagram? That is a thing. That is why I have not done it. But you can rest assured that it is not exactly the second derivative, because we have left this term, truncation error we have left. Okay? Then there is something called mixed derivative. Okay? Mixed derivative also, you can calculate it, and the mixed derivative means is what we are talking about, del u by del x and del square by del y. This is the mixed derivative. We have talked about del u by del x, okay? Del square u by del x square. Now we are talking about this. Okay. So how do you do it? You write equation. This is the same equation for Taylor series equation, and we find the derivative of this, partial derivative of this equation. We will make a derivative of this equation, and you will get these two equations where the y derivative will be there. Okay, and every term is found, the derivative is done. Okay, now what we will do, we will subtract these two equations. I mean, from 28 we will subtract 29. Okay, so what you will get, you are subtracting, you see the left side, you are subtracting this. Okay, or on the right side, this will go away, these two terms will go away. You are subtracting these two equations from, you are subtracting 29 from 28. So these two terms will go away. First term on the right side, they will go. First term on the left side, they are subtracted. And of course, on the right side, the second term, they will subtract from each other, and you will get equation like this. Okay. Now, what you will do, again the same thing we are doing, we are making n equal to 1, we are taking out, or n equal to 2, 3, 4, we are putting it here. And here again one thing, for n equal to e1, this will vanish. Okay. So once you do this exercise, what you get, this is your second derivative, mixed derivative. Okay, and this becomes equal to, and this is the order of error. Okay, so now what you are getting, the second derivative, mixed derivative, is written in terms of these two, and these two can be written in terms of central difference method. They are the first order derivative. Okay, so what we do, we put this value, and you can just, I'll give you these things, you forget about it. Finally what you will get, you will get this term. There will be 4 terms, this, and this. Okay, so the mixed derivative will be these terms, some मैं conceptually आपको बता देता हूँ. So what was happening is this is the second derivative, mixed second derivative. Mixed second derivative, and here we divide by del x and del y, and these are the 4 terms, and this is the order of error. Here there is some problem. What is the order of error? We cannot find directly, because now we are making two derivatives, so there are two terms of truncation. Okay, on the x side this is the second order, on the y side actually there is a cubic derivative का जो difference है ये, one is at I plus 1, one at I minus 1. This will actually increase the order by 1, तो ये delta y square जो है that will actually become delta y cube or so. Okay, so it is slightly complicated. So we can forget it because in any case we are leaving those terms. We have left all these exercises to the real heroes of CFD. We are just trying to understand what is happening. So there is an error because of delta y, there is an error because of delta x. We are finding mixed derivative. So delta y will also lead to some error, delta x will also lead to some error, and we are leaving out that. But interesting thing is that the second derivative at this point is found in terms of these neighboring. So mixed derivative at a point is written in terms of, you can say, 4 points, left and right, top and bottom of a current point. Okay, this you can see here, these 4 points. Okay, so on the left side is derivative, and this derivative is point I comma j, and rest all is on this. So the whole exercise in the nutshell is you are converting your derivatives into algebraic terms. That is one thing you are doing. And for all of them, all the 4 which we have done, 4 or 5 we have done. First order forward difference, first order backward difference, first order central difference, second order of second derivative, central difference of second derivative, and now this is again central difference, and you can say second order central difference of mixed derivative. Okay, in all these cases we are using Taylor series. In all these cases, first step we are doing, we are converting derivative into algebraic equation. In all cases we are using Taylor series. In all cases we are leaving certain terms which are called truncation error, and the order of that term, the highest most significant term in the terms which we have left, that is the order of truncation error. This is what we are doing. And this was about the points which are inside, so that you can have left and right, top and bottom point. But what if your point is on the boundary? If you are talking on the boundary, you can either go left or you can go to the right. You cannot go to central difference method, right? If you want a higher order of error at the boundary point, what do you do? There are options, the techniques are for that. Okay, so the boundary points are dealt differently, but we will do that in the next class. But so far what we are doing it for the points which are inside, right? And obviously when you will write the equation, you will write the equation for the boundary points also. You will move from one end to other end. So what do you do when you are at the boundary and you want to improve the accuracy? You want the order truncation error of the order of 2. What do you do? We will do it next time. There are some techniques for that also. So this is how we go about doing it. With this, we will end up one second phase, that is to convert, you can say discretize the governing equation into algebraic equation. or rather I would say in the second phase we are discretizing the domain as well as the equations. Once we have done, then we'll do as a sample one equation which we will discretize. Equation. So far we have discretized the derivatives. We'll discretize a simplest equation, only one, to see what happens. And after that we will see that how to solve those equations. If there are many equations like that, how to solve them. This is how we'll go about. Okay, then we stop here.